Okay, so here's the first quiz question that was due today. It definitely draws on the content we were talking about on Monday more than anything. So we'll talk about some synthetic strategies and the use of the Grignard reaction, because the Grignard reaction is pretty versatile. It can allow you to do a lot of different syntheses and make a lot of different structures. So one of the key patterns I see here is when I see I'm trying to make an alcohol, one of the first things I want to think about is, could this have been made from the Grignard reaction? Because if you recall, the Grignard reaction we talked about on Monday involved a carbonyl compound, so it would be a CO double bond. Could be a couple different R groups here. Maybe one of them is a hydrogen, or maybe both. And then the Grignard itself is, I'll make this a second R group. The Grignard itself is some R group, some grouping of carbons bonded to a magnesium. And then that could have a chloride or a bromide. It's basically a spectator counterion. So the key thing here is that the carbon of the R group that's directly sharing electrons with the magnesium has a very low electronegativity, and it really needs to give away those electrons to the carbon to make its noble gas configuration with the 2+. So you can think of a Grignard as a carbon nucleophile. So far, the only carbon nucleophiles we've seen were introduced last semester, where we had an alkynyl or an alkynide nucleophile, and we said, well, we can work with a primary alkyl halide that would have a leaving group here, and we can get that to attack. That's pretty limiting, because the only variety there we have was the leaving group had to be on a primary carbon, and we had to set it up as an SN2. Because this also acts as a base, it could also do elimination. So the Grignard is similar. Instead of a full negative in a compact sp orbital that's relatively stable, here we have a very large partial negative on a carbon, and this could be any type of carbon group. So that gives us a lot more versatility. And that carbon group, it doesn't have to only attack a primary site, it can attack any carbonyl, any site that's even somewhat partial positive or electrophilic, whether that site has a leaving group or whether that site is a CO double bond, and the new electrons will come in and form a bond there and push those electrons up. That we talked about as an option. So R3 would come in there, push those electrons up, and that's a nice option for producing an alcohol, because once this reaction occurs and it's very product favored, then in a second step, water and or H3O plus can provide a proton that oxygen can pick up, and that will give you an alcohol. So when you see an alcohol, you can work backwards from there and think about what reagents must have come together to form this new carbon-carbon bond. So when I see an alcohol, one thing I look for is the carbon that the OH is directly bonded to, that carbon. I'm going to think about one of the three groups attached to that carbon having come in as a Grignard to attack. So if I'm trying to make this product, I probably want to take off the largest one, as that breaks the molecule into similarly sized pieces. They're probably both relatively economical to purchase and work with. It doesn't really matter too much. In this particular question, though, I am required to start with reactants that have 5 carbons or less. So if I notice that this ring has 5 carbons and that the rest of the chain has 5 carbons, if I start with the ring and bring it in to form this bond, that will make a 10 carbon molecule very quickly from starting with 2 5-carbon pieces. So the idea is they're working backwards. If I start with the 5-membered ring and I make this carbon here connected to a magnesium, that would make this carbon nucleophilic. And it would attack the other carbon if the other carbon could accept those electrons by shifting electrons out. So the other molecule that I would want to add to that would have a CO double bond at that site. So I'm basically recognizing there's a carbon-carbon bond here, thinking about that bond could be made if I start with one of those molecules as a nucleophile and the other piece as an electrophile. So when you see an alcohol, the carbon that the OH is attached to was probably initially a CO double bond, or at least it could. That's one possible route you want to consider. If I consider that CO single bond used to be a CO double bond, and I push one of the carbon groups out retrosynthetically and make that a Grignard, well, then I recognize that carbon will take these electrons from the magnesium and it will use them to attack, to push these electrons up. And so that will put me basically in the structure. It's just that the oxygen will be negative. So after I do that, I'll need a second step where I use H3O plus and water to provide the proton for that oxygen to become protonated. So that's your best bet for that solution to that particular problem. And so this question here really kind of relates more to what we're going to do next week, but it also includes a Grignard reagent. So I thought it would be worth practicing and taking a look at now, since we just talked about the Grignard reaction, to really hopefully solidify that reaction in your minds. So in this question, I definitely want to start by counting the carbons. So 1, 2, 3, 4, 5, 6 carbons to begin with. And then I've got to add 7, 8, 9, 10. I've got to add 5 more carbons. So I'm seeing that this question is asking me to start with this piece of the product bonded to a chlorine. And I'm going to introduce the other piece. So this is a little different from the last one. If I have an alkyl halide, like a chloride or a bromide, I could start by using magnesium and ether to convert that into a Grignard reagent. And so the idea there is the magnesium has a pair of electrons. If it's neutral, which is what I would have to use, neutral magnesium metal, it's going to basically use those electrons to form a bond here, and the chloride is going to leave. So whether that happens by SN1 or SN2, or maybe a free radical mechanism, we don't worry about that. That's really more than we have time or the need to consider. But these electrons are going to end up here. And the key there is carbon 2 here initially is kind of electrophilic, because if the chloride leaves and produces a carbocation, something else will need to bring in electrons. And that's basically what the magnesium will do. Well, once the magnesium does that, then again, because the magnesium has such a low electronegativity, and even more so because it needs to make a noble gas configuration by getting rid of these electrons, they're pretty much on the carbon. So you can think of a Grignard as being a situation where you have a carbon that basically acts as if it's negatively charged, because the magnesium would be more stable away, making its noble gas configuration. So the carbon can act as a nucleophile. So if this is carbon 2, and I want that carbon to connect with carbon 7, I might think about adding a carbonyl. So this would be 7, 8, 9, 10, 11. So if I start with a carbonyl and carbon 7, we can do the reaction we just talked about. The Grignard would come in, push these electrons out, and that would give me this resulting intermediate. Gives me the correct carbon backbone, but this oxygen is on carbon 7. And so it's not in the right spot. So I'm realizing that this is not going to work in the same way that the previous quiz question worked. So there's a lot of variety with the Grignard. That's a good thing. It gives you more options. But from a perspective where you're trying to learn how to use it, it makes it challenging because there's so many different ways it can be used. So one thing you can do with the Grignard is have it attack a CO double bond. If the Grignard attacks a CO double bond, then the atom that was attacking the Grignard's carbon will end up directly connected to the carbon where the oxygen ends up. In this case, though, the carbon that we can make into a Grignard ends up 2 atoms away from the carbon that the oxygen is connected to. So this is a slightly different situation than what we just saw. So here's what we want to do with that. If you want your Grignard to end up connected 2 carbons away from an OH, the best move there is to use an epoxide. So just to contrast, if you want your Grignard to end up connected to the same carbon that the OH is on, you'd use a carbonyl because the Grignard would attack that very carbon, push electrons up, and then once the oxygen's protonated, you'd have the OH. If you want it connected 2 carbons away, if you want a 2-carbon chain between the OH and the R group, then you use an epoxide. Talked about epoxides last semester. We said they are somewhat electrophilic because the ring strain here, which results from both torsional strain and angle strain, makes this unstable. The Grignard can attack, and that will open up the ring. And note that if it attacks carbon 1, the oxygen will break its bond to carbon 1, but the oxygen will still be bonded to carbon 2. So that's how I get the Grignard to connect to a carbon that's 1 away from the carbon where the OH ends up. That's what we have here. Here's my Grignard carbon. Here it is. There's a 2-carbon chain between that carbon and the oxygen. So I want to set this up as a Grignard. So I would start by using magnesium and ether. And now we convert the alkyl halide into an alkyl magnesium halide. Now it's a Grignard. I want to get it to attack an epoxide that introduces all the remaining carbons that I want to include in the structure. So we said we need 1, 2, 3, 4, 5 new carbons. So carbons 1 and 2, 3, 4, 5. Carbons 1 and 2 are going to be connected by an epoxide. And so now due to sterics, this carbon with this pair of electrons is going to use that pair of electrons to attack the less sterically hindered site to avoid the steric repulsion that would otherwise occur during the transition state. And that's going to break this bond open. So the Grignard carbon ends up connected to carbon 1. The bond between carbon 1 and the oxygen breaks. It goes to the oxygen, but the bond between the oxygen and carbon 2 remains intact, and then 3, 4, and 5 are brought along as well. So that would produce the product, in effect, except it wouldn't yet be protonated. So after adding that epoxide, which would be my second reagent, the third thing I would do would just be to add a proton source to protonate that oxygen. There are other ways you could potentially do those syntheses, so I'll definitely be looking at your quiz answers, and if you're synthetic route is reasonable, I would definitely give you credit. If not, obviously I'll give you comments. Any questions about that? All right, well, let's go ahead then and get into the rest of chapter 13 here. So we talked about naming alcohols, the properties of some alcohols, including boiling point, solubility. We talked about how to make alcohols through a variety of reactions we talked about last semester, as well as now reduction reactions like sodium borohydride, lithium aluminum hydride, and Grignard reagents. And so this next section is about phenols. It's a really short section. I'm not going to probably ask you a question about this. I don't think there's a bullet point that even relates to it. This is just showing the industrial synthesis for phenol. So phenol has a variety of uses in industry. And it's made from benzene, which comes from crude oil through distillation. And so these reactions, we're not going to go through the mechanism, but this just shows you the synthetic method that industry mainly uses to make phenol. It also makes acetone, which is also valuable, and so they separate those two, and also they can sell the acetone as a commodity as well. So that's more informational than anything. So what are some reactions? What are some of the reactions that alcohols undergo? Well, we learned a few last semester. Last semester we saw in chapter 7, this chapter about substitution reactions, that HBr can be used to convert an alcohol into an alkyl halide, whether it's on a primary, secondary, or tertiary carbon. HBr can do that. Although the mechanism may vary depending on the sterics of the carbon, right? So when we're using HBr in the presence of an alcohol, the oxygen of the alcohol will first pick up a proton from the very strong acid, HBr, and that will produce a Br minus, which is relatively stable, but also a decent nucleophile. So once the OH is protonated, it becomes a good leaving group. If it's on a primary carbon, it can't leave first because that would create an unstable carbocation with very little hyperconjugation or induction to stabilize it. So that protonated oxygen or water leaving group would have to remain intact until the nucleophile collides and pushes it out in an SN2 single concerted step. And so the nucleophile attacking, pushing out the leaving group would create the new alkyl halide. Right? So if you want to convert an OH into a Br, that's one way to do it. If it's on a tertiary site, well, then it's too crowded. As we know, a nucleophile can't attack a tertiary carbon due to how crowded it is. So in that case, the leaving group would have to leave first to produce carbocation. Then the Br could come in and attack from either the top or the bottom, and you would get the product. So let's look at some other options. What are some other reactions that can convert an alcohol into an alkyl halide? One is using a zinc halide. And so what happens here is the oxygen's lone pair attracts to the zinc. So this zinc has a 2+ charge. The zinc does not have a noble gas configuration. If it was like magnesium and it already had a noble gas configuration, it wouldn't really very strongly attract new electrons in. But when zinc picks up new electrons, it's not breaking or affecting its noble gas configuration, so it has a decently strong attraction for electrons. It's not super strong, but it's strong enough where this can form an equilibrium. And if some of the molecules look like this, it's similar to a water leaving group. It's not obviously a water leaving group, but it's similar in that when the oxygen shares a lone pair and makes a third bond, it only has one lone pair, it takes on a formal positive charge. And that formal positive charge attracts electrons much more strongly from the carbon, creating a nice big partial positive on that carbon, and that can attract a nucleophile in. So we would probably have extra chloride ions here, maybe by adding NaCl or something like that, but they also would be in solution due to the only being ionically associated with the zinc. So any chloride in solution could then attack and push that leaving group out and make the alkyl chloride. So very similar to HBr, except the oxygen is picking up a zinc instead of a proton from HBr or HCl. By the way, HCl would work here as well as HBr. So if you want to make a chloride, you'd use HCl. If you want to make an alkyl bromide, you'd use HBr, obviously. If you want to convert an OH into an alkyl halide, you could also convert it into a tosylate leaving group first, right? We talked about this reaction a fair amount. If you OH, which is not a good leaving group, you can get the oxygen to attack the tosyl group, which would push out the chloride. And then this pyridine is a base, it would pick up that proton. And so you would have a TS there. And the TS makes the oxygen a good leaving group because if it leaves, it can stabilize the resulting negative through resonance with 3 different oxygens, if you recall the structure of the tosylate group. And that now makes it susceptible to attack. So on a secondary site, it's not too sterically hindered. If I have a halide, like a chloride, or a bromide, or an iodide, those are only a single atom. They're not very sterically hindered, so they can usually come in here and attack. If the attack occurs as the leaving group's leaving, that's an SN2. And the attack would have to happen from the opposite side from where the leaving group leaves. So if the leaving group's facing out at me, the nucleophile would have to come in from the back side. Right? So that's why I get inversion of stereochemistry if an SN2 occurs. In this particular example, I might also get some of this. So how would I get X to come in and replace from the same side where the leaving group left? Well, that would require it to go through a carbocation intermediate. If you recall last semester, we said when the leaving group's a good leaving group and it's on a secondary position, it's not too crowded for the nucleophile to come in and do an SN2 and end up in opposite spatial arrangement from where the leaving group left. But also, if the leaving group happens to leave first, it's also not too unstable to form a carbocation due to the extra hyperconjugation and induction compared to this super unstable primary carbocation. So that could happen, and then if that carbocation forms, it's going to be totally flat, and so X could come in from the front half the time and give this product, or from the back side half the time and give the other product. So this would still be my major product because it forms through both SN1 and SN2. And this one only forms when SN1 occurs, it forms half the time. So it will be a smaller percentage of the product compared to the other one in the secondary carbon situation. So that's a reaction you might want to use at some point as well. Here's another way to convert an OH into a halide. SOCl2 or thionyl chloride. So here's this Lewis structure for thionyl chloride. The sulfur actually has a lone pair even though it's not shown here. It's not really involved in the mechanism, which is probably why they left it out. But the oxygen here is very electronegative compared to sulfur. So the sulfur, despite the lone pair, has a large partial positive, and that attracts in the lone pair from the oxygen. So the oxygen attacking here, pushing electrons out to this other oxygen, creates this relatively unstable intermediate because it's got these formal charges. But one of those charges can quickly be stabilized if electrons swing in and push out a stable chloride leaving group. When these electrons swing in, the oxygen could also leave, right? The positively charged oxygen is also a great leaving group, and that would just go back. And then once in a while, the oxygen would attack again, and then it would go forward. So sometimes this intermediate, when the electrons swing in, it would push out a chloride and get to the next intermediate. And then the pyridine, like we've seen before, serves as a base. If it picks up this proton, leaving electrons behind, that would stabilize the oxygen. And now, basically what you've done is converted the OH into a much better leaving group. So it's not a tosylate leaving group, but it's a great leaving group. So the chloride that left earlier now can act as a nucleophile, and when it comes in here, it can push out that leaving group. And what's great about this leaving group is it can't come back in. because when the leaving group leaves, it's not just leaving, it's also breaking apart. So this pair of electrons would swing quickly in between the oxygen and the sulfur, and that would push out a chloride. And that produces SO2, right? This is SO2, and that's a gas. And the chloride is also really quite stable. And the SO2 gas bubbles out, and so it can't come back in and do the reverse. So each one of these steps is reversible, except the last one helps to drive the entire equilibrium toward the product side. So that's a good way of replacing an OH with a Cl. So that's another option for making an alcohol into an alkyl halide. And then here's yet another option. You want to be familiar with each one of these sets of reagents and the mechanisms, in case you're asked about that. This one's relatively straightforward. You want to make OH into a better leaving group? Give it a positive charge, right? That's this theme we've been seeing in these last few slides. Right? I can protonate an OH to give it a positive charge and make it a better leaving group. I can tosylate it. That doesn't give it a positive charge, but it does make it a better leaving group because the negative that forms when it leaves is stabilized through resonance. I can have it pick up a zinc. That gives it a positive charge, makes it a good leaving group. I can have it attack the sulfur, which gives it a positive charge, but then that's usually deprotonated. So it won't usually leave until this point because that positive charge is really relatively unstable, and the pyridine usually quickly deprotonate it. Usually a proton transfer happens more quickly or more often back and forth than a nucleophilic attack, so that would usually happen in the next step. But in this case, it's a very similar situation. The phosphorus also has a lone pair, but phosphorus is like hydrogen. It's very low electronegativity. So when a bromine or chlorine is bonded to it, it really pulls electrons away and creates a fairly large partial positive on the phosphorus. And so that attracts the fairly large partial negative on the lone pair, which enables it to form a bond and push out a Br. The Br that leaves is now a nucleophile. And now the oxygen is bonded to phosphorus, and so with 3 bonds in one lone pair, it takes on a formal positive. The bromide can attack and push that out as a leaving group. And so then essentially you've replaced the OH with the Br. So just to point out here too, this is an SN2. If it's a primary site especially, the Br would have to come in as that leaves, and that would be an SN2. All right, so let's say I want to convert this compound into this compound. I want to make the OH leave, and I want to replace it with a Cl. So that's actually a little more complicated than it might seem. If all I do is add, say, HCl, which would be my first instinct if I thought about replacing an OH with a Cl, what's going to happen is the OH is going to pick up a proton from the HCl, it's going to make that into a much better water leaving group. Oops, there'd be another proton there now. So since it's a secondary carbon, it could leave. If it leaves a secondary carbocation, half the time the Cl- would come in from the front, and half the time it would come in from the back. So I would only get half of my molecules at most converted into the desired product. But since Cl- is a pretty small individual atom rather than a grouping of atoms, a lot of the time it would probably just come in and push that out in one step. It's not too sterically hindered because it's only secondary. It's not too, like a tertiary would be too sterically hindered for the nucleophile to attack there. So if it does attack, it would have to attack from behind to push the OH or the water leaving group out the front. It can't come in on the same side where the leaving group's leaving. If it's doing an S2, it has to do backside attack. So most of the product, in that case, would have the Cl with the wrong stereochemical or spatial positioning. So if we want the chloride to have the backside attack, we need a couple more steps. So that's the idea here. If we want the chloride, in other words, to have the same spatial positioning as the leaving group, we really got to kick the leaving group out and then kick that leaving group out. We can do two SN2s, right? One would do inversion of stereochemistry and the other would invert it back to the original stereochemistry, right? So that's the idea here. So what reagents do I need to complete this? If I want to go from OH to OTS, I use tosyl chloride and pyridine. So that would make that into a great leaving group. If I want to push it out with an OH, I would just use NaOH. And now this is a good leaving group. OH minus is a strong nucleophile, so it would probably come in and push that out in one step. It's not terribly sterically hindering. So if the OH comes in and pushes that out, it would have to come in from the back side. The tosylate is blocking the front, so it would come in from behind, and that's why I would end up with the dashed wedge. Then if I want to replace that with a Cl, I've got a couple options. I've got the zinc chloride option. I've got HCl as an option. I've got SOCl2 as an option. Those are all reactions we just talked about. So you can look back at those and understand their mechanisms, but each one involves typically an SN2 in the last step. Whether I pronate that with a proton to make it a better leaving group, whether I have the oxygen attached to the sulfur first to make it a better leaving group, or the zinc, either way I'm going to have a Cl minus coming in there from the back side to push out whichever leaving group I create. And since the leaving group's positioned away from me, the chlorine would have to come in from the front, and that's how I would end up with a solid wedge there for it. Questions about that one? All right. All right, so what are some other reactions we learned that alcohols can undergo? Well, in Chapter 8, we talked about elimination. So there's really two ways to eliminate an alcohol that we talked about. And one is this acid-catalyzed dehydration. So in this situation, we use the concentrated acid, because water is a byproduct of the reaction. If we have a lot of water, since that's a product, by Le Chatelier's principle, all that extra water would shift the equilibrium back toward the alcohol side. So if we want to convert an alkene into an alcohol, we do the same reaction. We use an acid catalyst, but we use lots of excess water, since that's a product or a reactant in the reverse direction, to shift it back toward the alcohol. If I want to shift it in the forward direction, I don't want that water. So I use a concentrated, strong acid with a non-nucleophilic conjugate base to pronate that and make the oxygen a better leaving group. The resulting conjugate base of the sulfuric acid is really stable and unreactive, so it won't do anything. But then what will happen is, if it's tertiary, especially, the water leaving group will leave behind a carbocation, and another water will pick up a proton to regenerate the catalyst, shifting electrons in to form the alkene. The limitation here is, if you have an OH that you're protonating with an acid to make it a better leaving group, it will usually leave first, assuming it's not a primary carbon, because that would produce a carbocation that's too unstable. As long as it's secondary or tertiary, where it can decently stabilize the carbocation, the water leaving group should leave first. And when that does, you're going to get a carbocation. So there's the possibility of that carbocation rearranging. Not in this example, but if there was some way to make the carbocation more stabilized through resonance or hyperconjugation or induction, it would rearrange through a methyl or hydride shift potentially. If I want to make the alkene here, giving this product, I can't really do that with this reaction, because what's going to happen is water, which is the best base around under these acidic conditions, it could pick off this proton, But as those electrons would swing in to start to form the pi bond here, since it's only substituted with 2 carbon groups and 2 hydrogens, it's not going to be as stable as it's forming as it would be to form the pi bond in a position where it's more substituted with carbon groups and fewer hydrogens. So the major product that happens more often and is also thermodynamically favored would occur when the base picks off whatever proton produces a more substituted pi bond. So if that's the pi bond you want, great. And we did this reaction last semester in lab, and that gave a pretty good yield, and most people's NMRs looked really good to show the product looked relatively pure. It's a pretty successful reaction. But if I want the other product with the less substituted pi bond, this is not the method to use. Why is E2 unlikely here? Because we have a weak base. The base is weak, it's water. It's not a very strong base, so it usually won't get involved until after the carbocation forms. So if you want to make the other product, you need the other method. So the other method we talked about last semester for converting OH into an alkene was to first tosylate it to make it a better leaving group, and then use a strong base. The strong base promotes an E2. And I can take advantage of the fact that the steric hindrance of the R group on my OR minus can sometimes determine which beta hydrogen is removed to complete the elimination, right? So in this particular case, this is my alpha carbon. I've got 1, 2, 3 beta carbons, and they're all equivalent. So it doesn't matter which of those a hydrogen is picked off of, but the base would pick off a hydrogen from any one of these 9 hydrogens on the outside here, push electrons in, push that out, and make the alkene. What if I was looking at that reaction from the last slide, though? What if I had this, and I used tosyl chloride and pyridine to convert that into a tosylate leaving group? Now, if I want the alkene to form here, I can use a smaller strong base to pick off this proton once it's anti-periplanar to the leaving group, push electrons in, push out the leaving group, and make the pi bond there. And a strong base should do that because, as we said in the last slide, the pi bond in this position is more stable because it's more substituted with carbons than if it's in the other position. If I use a more sterically hindered base, though, like the terp-butoxide, which looks like this, the terp-butyl group is very sterically hindering, so it's going to be harder for this base to come in and get the same proton. If it goes in for the same proton, the sterics of this group might bump into some of the sterics on the ring or the methyl group over here, and that would create a repulsion, so it's not going to happen that often. It'll be unstable during the transition state. Instead, it'd be more likely to go for the hydrogen that's on the outside and more available with no sterics. And that would push these electrons in and push the leaving group out and give you the other alkene. So you definitely want to make sure you understand how to control the regiochemical outcome of an E2 elimination by using a less or more sterically hindered base. We don't expect any rearrangement here because there's no carbocation forming. It's just one step. Whichever beta hydrogen can be removed through the lower energy transition state will be removed to push out the leaving group. All right, so that's a review of the reactions we've already seen for converting alcohols into other functional groups, as well as a couple new ones. And so now we're going to see another entirely new reaction that alcohols undergo, and that is oxidation to a carbonyl. So if you have an alcohol and it's either primary or secondary, So this one's secondary. You could also imagine a primary one. As long as there's at least one hydrogen bonded to the carbon that the OH is attached to, there's a possibility that with the right reagents, that hydrogen could be removed. It's not there anymore in the product, and we can make a CO double bond. So this is the reverse of the reactions we talked about yesterday or on Monday, right? We said if you have a carbonyl and you want to reduce it, you need to deliver a hydride. So either NaBH4 or LAH would deliver a hydride into that, push the electrons up to make this product, and then obviously oxygen would need a proton source to pick up a proton. So if we want to do the opposite, we need a reagent that can remove a hydride. Something that will take the hydrogen, not the proton, not just the nucleus of the hydrogen, but the electrons as well. We need something to pull these electrons away so that the oxygen can swing back down its lone pair and reform the double bond and then be deprotonated to make sure that it's neutral. All right, so that's the process we're going to talk about next. So generically, without talking about the reagents yet, if I had a primary alcohol, I could remove one hydride, reform the double bond to make an aldehyde. Depending on the reagent I use, it might also be strong enough to remove this hydride, which would allow that to be replaced with another oxygen. So we're not going to talk about the mechanism for this in too much detail because it's very complicated and there are tons of steps in these oxidation mechanisms. So to avoid you having to memorize an extremely long mechanism, we're just going to have to ask you to memorize some of the outcomes of these reactions and the sets of reagents. So unfortunately, that may require some memorization for you, but again, practice and frequent use will help you remember those specifics. So just to let you know, if you have a secondary alcohol, there's only one hydride to remove. So if the oxidizing agent removes that hydride and the oxygen is able to swing its electrons back down to reform that, that's basically it. You can't further add more oxygens. The carbon-carbon bonds are not easily broken like the carbon-hydrogen bonds are in these mechanisms. So one specific compound you can use is called chromic acid. Oh, also, if you don't have any hydrogens, then there's pretty much no reaction, right? Because we don't have a hydride to remove. So the oxygen, it can't swing its electrons back down and reform a CO double bond if there's nothing to push out. There's no hydride to remove. So chromic acid is a common reagent used for oxidizing alcohols to carbonyls. And that's formed by taking chromium trioxide and sodium dichromate. And the chromium trioxide can react with water and H2O+. The dichromate can react with sulfuric acid and water. So basically, these two are two different ways to show the same reagent. So there's actually three ways to show this reagent. If you show this combination, if you show this combination, or you just show the chromic acid, you want to get used to recognizing this reagent in any one of these forms. Some textbooks will use this format, some textbooks will show it this way, others will just say H2CrO4. That's probably how you'll see me draw it. So if I'm expecting you to recognize primary or secondary alcohol being oxidized using chromic acid, I would probably just write H2CrO4, which is the formula for this molecule. So here's a bit about how it works. So what would have to happen here is a connection between the oxygen and the chromium. So we need to set this up so that we have to take a pair of electrons away. So what I was showing on the last slide was actually a little bit backwards, which obviously seems silly now in retrospect, because just to point out, what I was suggesting was if the hydrogen takes the electrons away, that would be the opposite of delivering the hydride. And that makes sense from a standpoint of just thinking about the electrons, because then the oxygen could swing a pair of electrons back in and reform the double bond. However, that doesn't really make sense from an electronic point of view, because hydrogen is much lower in electronegativity. It's lower than carbon, especially. It's not going to take electrons away. It's very difficult for hydrogen to pull electrons away when it has a lower electronegativity. So that's not really the movement of electrons that occurs in the mechanism. I was just using that to show how the process is the reverse of the reduction reactions we saw on Monday, where the hydride brings electrons in. Basically, in essence, electrons have to be removed. But typically, the hydrogen isn't removing them. So what's happening first is an OH and an H here are removed from their respective positions to form water. And the steps involved in that are numerous, and we're not going to discuss them. So after that occurs, this oxygen can connect directly to the chromium, which is the bond we see here. And then that intermediate is now set up for the oxidation to occur, because now even a weak base can pick off this proton, and these electrons can swing in to make the CO double bond, and then the chromium can take the other electrons, so the oxygen doesn't make more than a noble gas configuration around it. So again, you don't really have to know the mechanism here. It's just hopefully helping you get a visual representation to show that the alcohol is being converted into a carbonyl by removing that hydrogen and removing a pair of electrons, so the remaining electrons can complete the noble gas configurations without needing the hydrogen present there on the carbon. So from a practical point of view, we said we can oxidize a secondary alcohol, and this chromic acid does a great job of converting a secondary alcohol into a ketone. We also said you can oxidize a primary alcohol to an aldehyde, and potentially an aldehyde to a carboxylic acid. So here there's a couple reagents depending on your goal. If your goal is to convert the primary alcohol into the aldehyde through a similar mechanism from what we just saw, and stop there without going further, if you're trying to make the aldehyde, then you need a specific reagent. It's called PCC, or pyridinium chlorochromate. This will stop at the aldehyde. So it's not as strong of an oxidizing agent as the chromic acid that we just saw. The chromic acid will react with aldehydes in the same reaction we're seeing here. It will convert an aldehyde into a carboxylic acid. So it's actually a slightly different mechanism. So if you want to make an aldehyde, but you're using chromic acid, it won't last. It'll just react and form a carboxylic acid. So we need pyridinium chlorochromate, which is this compound here that's formed from pyridine reacting with a chromate and HCl. This combination with the pyridinium lowers the reactivity of the oxidizing agent. So it's reactive enough to oxidize the primary alcohol to the aldehyde, but it's not strong enough of an agent to convert the aldehyde into the carboxylic acid. And so you want to do enough practice to remember that PCC specifically is the one reagent you need to know that will convert a primary alcohol into an aldehyde and then stop reacting. So really any primary alcohol can be converted to an aldehyde with PCC. PCC can also be used to convert a secondary alcohol to a ketone, along with also the H2CrO4. So H2CrO4 could be written in that form, or it could be written in the form of the reagents that are used to make H2CrO4. But either of those sets of reagents are the same, and they will oxidize a secondary alcohol to a ketone. PCC will also do the same thing. PCC won't further react any carbonyl. It won't further react an aldehyde, it'll stay as an aldehyde. All right, so what would be the product of this reaction? We've seen some examples here using the chromic acid reagent. I think this is meant to be excess. So the abbreviation for excess is usually XS, not EX. But if I'm using excess, basically we just mean that the excess can react. Any site that's reactive toward chromic acid would be fully oxidized. So here I've got a secondary alcohol. That's reactive toward chromic acid. So I expect, let me just number the chain. I expect carbon 2 to be oxidized from an alcohol to a ketone. Carbon 6 is already a carbonyl, but it's an aldehyde. As long as there's still a hydrogen on that carbon, the stronger of these two oxidizing agents will continue to oxidize it. So I expect carbon 6 to be converted into a carboxylic acid. And then here I've got a primary alcohol on carbon 4. There's another carbon. And then this OH that's on that carbon is also susceptible to being oxidized. And since there are two hydrogens to remove, those would both be removed, and I would expect that to also be converted into a carboxylic acid. So with the stronger oxidizing agent, primary alcohols and aldehydes both end up converted to carboxylic acids, and secondary alcohols end up converted to ketones. There's a couple slides here about some of these biological oxidizing and reduction reactions. And NADH is a very common reducing agent. So here's the structure of NADH. It has a sugar here, it has a DNA base, it's got a phosphate linkage, and then another sugar. So these molecules are finely tuned through evolutionary process to provide solubility and interactions with other chemicals. What makes this a reducing agent is that it has the ability to deliver a hydride. So these two hydrides can be given away. And so looking at that reaction, so basically all the stuff in gray here is represented by this R. Right? So that stuff's not reactive chemically, at least in these redox processes. So what would be happening here is the lone pair of the nitrogen would swing in, push those electrons over. That would actually push out a hydride. So as I was saying, most of the time hydrogen's not electronegative enough to pull electrons away from a carbon. And that normally would occur through a pretty high energy transition state and be very unlikely to happen. So what allows this to happen in a biological process is an enzyme. Right? So an enzyme will catalyze this process, meaning it will stabilize it as the bonds are breaking and forming to allow it to happen much more often than it normally would, which is very rarely. So delivering the hydride into the carbonyl, similar to how LAH or sodium borohydride deliver a hydride to a carbonyl, it'll push the electrons up and pick up a proton. And so that is how nature, or at least in humans specifically, and I think in most animals, that's how animals convert carbonyls into alcohols, if they need to do that for whatever biological reason. Just like most biological processes, it's reversible. So if you start with the alcohol and your body needs to convert that into a ketone, what would happen is this same site that delivered the hydride would be able to accept it back. So the enzyme might have a basic site on it, or there might be a water or something other that basic compound that collides here. Notice in these biological reactions, I can get 3 different structures to collide at once. That's the beauty of an enzyme. An enzyme has been fine-tuned over many years of evolution to stabilize a collision between these specific molecules in a very specific way. And that plays a big role in metabolism, right? Because in metabolism, you have to convert your food into usable molecules that your body can use for energy or to build cellular structures or whatever. So these enzymes allow collisions, and in this particular case, electron swinging and pushing out a hydride so that the double bond can form without breaking the noble gas configuration of that carbon. And the NAD plus, which is an oxidizing agent, is able to take those electrons and shift the lone pair back to the nitrogen to alleviate that positive charge and convert it back into NADH. So shifting back and forth between NADH and NAD plus is one method that organisms have evolved to use to affect the energy of molecules, converting ADP into a higher energy ATP that can be used later to release that energy, as well as converting simple molecules from alcohols to ketones and vice versa. So you want to be a little bit familiar with that. There's a possibility I could ask you a question about that mechanism, or probably more likely about some of the concepts associated with that. As we were saying, a tertiary alcohol does not have a hydrogen to remove. So there's really no way to convert that into a CO double bond. The R groups can't be removed with an oxidizing agent. So obviously I'm not going to make a 5-bonded carbon. That's ridiculous. So whatever oxidizing agent I use, if I use an oxidizing agent on a tertiary alcohol, it's not going to react. It's just going to remain as an OH group. Phenol is similar in that there's no hydrogen here to remove, but there is a pi bond that could be removed. So phenol is actually oxidizable. It's even more readily oxidizable than a primary or secondary alcohol. And so just to point out, if you have a phenol and you use the chromic acid conditions, that will oxidize the OH group. It'll actually install a second oxygen, and you'll make this benzoquinone structure, which is pretty stable, depending on the oxidizing or reducing agent that you might add next. You can make hydroquinone. Quinones are very common in biological structures, so-called ubiquitous, meaning they're pretty much everywhere. They're found in all kinds of different biological structures, and so that would be a function group that might be more relevant in a biochemistry course, but it goes along with the theme that we've been talking about, so that's why it's included here. Probably won't ask you a question about that. Since this is organic chemistry, we're more interested in synthesis. We're more interested in putting reagents together and controlling the outcome. And so now that we've added some reactions to our bag of tricks, we can recognize we've got ways to reduce alkenes. We can shift those back and forth, reducing an alkyne to an alkene. We need the Lindlar catalyst to prevent it from going all the way to the alkane. If we wanted that to occur, we would just use hydrogen and platinum, palladium, or nickel as a metal catalyst. Now that we know this free radical reaction, we can put a bromine on here and do the elimination to make that into an alkene. We could add 2 bromines on with Br2 and do 2 eliminations to make the alkyne, so we know how to go back and forth here. And now we've added some new reactions. So we know how to reduce and oxidize alkenes to alkanes, etc. We can also go from alcohols to carbonyls, or from carbonyls back to alcohols, right? So the LAH reaction we talked about last class will convert a ketone into, or an aldehyde into an alcohol, and the chromic acid can convert a secondary alcohol into a ketone. The PCC is what you want to use if you want to go from a primary alcohol to an aldehyde. Let's skip this. So I'm not going to ask you questions about oxidation states specifically. This is a great slide. It comes directly from the textbook. I'm not going to describe it, but I just wanted to point that out, that the textbook does have a few pages, mostly at the end of each chapter, that kind of summarize a lot of the reactions that are covered. So if you're looking for ways to work through examples, you can rely on these. They're very useful if you're working through a problem and you're not sure how to get maybe from an alkyne to an aldehyde, or from an alcohol to an aldehyde, or from an aldehyde all the way to an alkane. You know, you can find your way through this flow chart and get from point A to point B. Eventually, though, you'd want to keep practicing until you get to the point where you're able to work with these reactions without relying on this type of flow chart. Obviously, you won't have it during exams, so you'd want to be able to practice enough to get familiar enough with the reactions. All right, so let's look at a couple examples. All right, so there's two syntheses here, both starting from this metal compound, working our way out. So how do I convert this primary alkyl bromide to an aldehyde? Well, we now know a way to make an aldehyde. The only way we know to make it is with PCC, starting from an alcohol, right? So we still have a few reactions that only work with one set of reagents. And if there's only one set of reagents we know to make an aldehyde, well, then we would obviously make it using that set of reagents. So I would have to make a primary alcohol into that, and that would involve PCC. And usually the solvent for that is dichloromethane. So how do I make the primary bromide into the primary alcohol? I would use NaOH. The OH minus would just come in an SN2 and push the bromine out, and I would end up with an OH there. What if I want to make that carbon not changing the carbon skeleton in either one of these reactions, but what if I want to make carbon 1 into a carboxylic acid? Well, I could start the same way. By using NaOH. If I get an oxygen on that site, can I then convert a primary alcohol into a carboxylic acid? Yes. Oops, keep doing that. The chromic acid. It's a stronger oxidizing agent. So you want to make sure you understand the difference between the PCC, pyridinium chlorochromate, and the chromic acid. PCC will oxidize a primary alcohol to an aldehyde. Chromic acid will oxidize a primary alcohol to a carboxylic acid. So I've got two different options there. Also wanted to point out on this slide here, this reaction here could also be done using a Grignard reagent. So we haven't discussed this yet, and we'll discuss this in more detail later, but just wanted to give you a preview here since we've been talking about the Grignard reagent. So I know I can convert this bromide if I use magnesium and ether as a solvent. The magnesium will come in, replace the bromide. That will make that a nucleophile. So now I want that nucleophile to attack a molecule. Oh, actually, no, that won't work. I was thinking in my mind. Oh, I got off on a bad track there, so just ignore that part. Pretend that didn't happen. Okay, moving on. So this is just a, a little review of what we talked about last time. We know that if we have a certain number of carbons in a structure, we can increase the number of carbons, making a new carbon-carbon bond using the Grignard reagent. So depending on the number of carbons I want to introduce, if I want to introduce only one carbon, I make that carbon a nucleophile by having it share electrons with magnesium, which means they're not really shared much. They're mostly on the carbon as a lone pair. That would attack, push electrons up, and then the water would supply the proton to give the alcohol, right? So we talked about the Grignard reaction. Grignards can attack any kind of carbonyl. If it attacks an ester, recall that the carbon sharing electrons with magnesium would attack here once, pushing electrons up. So the new methyl group would be here. Then now because there's a leaving group, I would expect those electrons to swing back in and push out the leaving group. Now the CH3 is still there, but the OMe is gone. And now that it's reformed a CO double bond, it's susceptible for another molecule of the Grignard to attack. So I can get two methyl groups in there instead of just one. And then later in the second step, the water would be used to protonate that oxygen and make it into an OH. So you definitely want to keep practicing with those reactions until you can get good with them and start to incorporate them into syntheses problems. All right, so what if you want to convert an aldehyde into a ketone? Oops. There's another pattern to recognize here, right? What's the difference between an aldehyde and a ketone? Well, basically we're replacing the hydrogen with an R group. So we have to introduce the R group and we have to remove the hydrogen. So that's two steps. So I would start with the Grignard to introduce the R group. Whatever that R group is, maybe a methyl ether, whatever, I would have that methyl or ether connected to magnesium. It would pull the electrons away from the magnesium and push these electrons up. And that would introduce the R group. Then in a second step, I would add water and potentially H3O plus to protonate that oxygen and convert it into an alcohol. So that introduces the R group, makes a new carbon-carbon bond, extends the complexity of my molecule. Once I have a secondary alcohol, though, I can add the chromic acid, PCC or chromic acid. Either of those reagents will oxidize the secondary alcohol to a ketone. So in a specific example here, just want to count the carbons, make sure I get the correct number. It's very easy to make a mistake with the number of carbons. So I need to add 5, 6, 7. I need to add 3 more carbons. So in the first step, I'm going to get those 3 carbons, 7, 6, and 5. And I have carbon 5 bonded to a magnesium. That way, carbon 5 will pull those electrons away from the magnesium and use them to attack the carbonyl and push electrons up. In the second step, I would add H3O plus and water to provide a proton for that oxygen. So after step 2, I would have installed those new 3 carbons, but my oxygen would be negative, would be an OH because I did protonate it with the H3O plus. So now my structure looks exactly like the product, except I have an OH here instead of CO double bond. So I got to remove this hydrogen and remove that hydrogen. That's a matter of oxidizing that structure. So then from a secondary alcohol to a ketone, I could do PCC or the H2CrO4 chromic acid. And that would oxidize the alcohol up to the carbonyl. All right, so that's really what we needed to get through today. We definitely want to practice with that. There's a lot of good practice here that I'm suggesting. Please let me know if you need help with any of that, especially if what you're seeing in the solutions guide isn't making sense. On Monday, we are going to ignore this. On Monday, we're going to get into chapter 14. So you want to prepare yourself with the readings there and some videos about ethers. Right, so an alcohol is an ROH, an ether is an ROR. So by replacing the hydrogen with another R group, that makes an ether. And so we're going to talk about ether chemistry starting on next week. So make sure you look at the day 8 quiz questions. Those should be due on Monday. Any questions about anything? Just want to double check that about the quiz questions. So I'm just going to open up one of these quiz question documents here. Ah, 7. Yeah, I thought that might have been a mistake. So just to clarify, on Monday, technically that's day 7. Day 7 questions are due Monday, and then there is no day 8. That's where we might normally have an exam if we had a normal scheduling. But since we don't have a normal scheduling where we could have an exam in our normal way, we're going to continue with what we've been doing. And so next Monday is day 7. Next Wednesday is day 9. So you'll have to do the day 9 quiz questions by next Wednesday at 1. All right, well, let me know if anybody does have any questions at any time.